Welcome everybody as we're going through getting the solutions on the West River Math Competition. Let's go ahead and answer each of these questions. Question number 1. A circle of radius 6 has a central angle of 60 degrees. Find the area of the sector of this central angle that it cuts from the circle. Now, many of you may not be at sector area yet or with circles. That's a chapter 10 topic. But once you do, you'll understand this problem a bit more. So we've got a circle, it's got a radius of 6. One of the best things you can do to solve problems is to draw them. Be like, here's a circle with a radius of 6, and it says it's got a central angle of 60 degrees. Now, central angle goes from the center, and it's 60 degrees. So maybe it's right about there. Okay, that's 60 degrees. And we want to find the area of the sector. In other words, what's the area inside this? Okay, we know that it's 60 degrees. Now, thinking about that 60 degrees, I also know what goes around the full circle. The full circle is 360 degrees, and that is 60 degrees. So I can do 60 degrees divided by 360, and I find out that it's 1/6 of the circle. So a sector is a small section of the circle. This one is specifically 1/6 of the circle. So how would I get its area? Well, I just take the area of a circle and I find out 1/6 of it. The area of a circle is equal to pi times radius squared, but the area of a sector of the circle is equal to the degrees divided by 360 degrees times pi r squared. In other words, it's a portion of the circle. Now, we already did this. We found out that that's 1/6. So the area of this sector specifically is going to be 1/6 pi times 6 squared. Now notice how it's 6 squared and 1/6. Those cancel out, and we're just left with 6 pi. And if you plug in 6 pi into a calculator, I believe it's approximately 18 point something. So let's find out real quick. 6 pi, 18.84. And we're going to round up to 8.5 because we are rounding. And the area has an exact answer, but it also has an approximation. Now, the last thing to check is the units. It says it's got a radius of 6. It's not 6 feet or 6 inches or anything. So our answer is perfectly valid. All right. And here we are onto the second problem. This says a parallelogram shown below has a perimeter of 26. We want to find its area. So let's take a look at it real quick. It's got a perimeter of 26. That means going around the entire outsides is going to be 26. Across the bottom, it's 3 and 5, but we don't know any other information. Now, in order to get the area of a parallelogram or any type of rectangle, one of the things we want to recognize is that this triangle could be moved to fit right there. And then it would make a rectangle. And so the area of any rectangle or parallelogram or square or rhombus is going to be equal to the length times the width, or typically, because it's a parallelogram, we call it the base times the height. So we just need to know the height, which is this length right there. In order to find that length, let's use the information that we have. Specifically, the perimeter is 26. So if the perimeter is 26, this is 5, this is 3. And because, it's a parallelogram, so these sides are congruent, these sum each to 8. So let's go ahead and put that there. That sums to 8. That sums to 8. All right. So if I know it's got a perimeter of 26, but the top and the bottom are 8, that's 16. So I can do 26 minus 16, and I get 10. Now, again, perimeter, opposite sides are congruent. So that means that this is 5 and this is 5. Automatically, I know something about this triangle. Now, in each class, you hopefully have begun to recognize Pythagorean triples. This is a Pythagorean triple. It's a right triangle where you know 2 sides and you can get the third by understanding that Pythagorean triple. Specifically, this is a 3, 4, 5 triangle. 3 squared plus 4 squared equals 5 squared. This is a 3, 4, 5 triangle. So we know that the height is 4. Now, in looking at this, we can go ahead and get the area of this rectangle by just being like, oh, the base is 8 and the height is 4. That is going to be 32. So the area is 32. All right, we'll go on to the next problem in just a moment. All right, and we're on to the next problem. This one is number 3. A regular octahedron has 8 faces that are equilateral triangles. How many edges and vertices does it have? Now, if you play some board games, you might be able to recognize this. 8 equilateral triangles. This is actually a D8 dice. You got a face like this, and then one like this, and then in the back you've got more, and then on the bottom you've got one like that and like that. And you've got 2 more on the back. So this has 8 faces that are equilateral triangles. How many edges and vertices does it have? Now, you'll learn about edges and vertices in chapter 11. The edges are the places where 2 planes meet. So if you look at the one that I'm holding right, or that I drew, we got 1, 2, 3, 4, 5, 6, 7, 8 that we can see. Doesn't mean it's only 8, but there's only 8 that we can see right now. We got to think about the back as well. And so we want to know how many edges it has. The second thing we want to know is how many vertices it has. Vertices are where 3 or more planes meet at a point. So vertices are like this point. And typically for a single one, we call it a vertex. So there's a vertex, there's another vertex. So you want to think about how many vertices there are. Okay, so how many edges does it have? We'll put down here edges. And over here we'll put vertices. Okay, so how many edges does this have? Well, we got 1, 2 faces, 3, 4 faces in the back. But the edges, notice how the edges are the meeting of 2 faces. So there's one here, there's going to be another one in the back, another one here, that's 3, plus another one here. There's 4 on the top. Then there's 4 going around the side, so we're at 8, plus another 4 on the bottom. So there end up being 12 edges. And I used the wrong color for that. How many vertices does it have? Well, there are 4 vertices across the middle, 1 at the top, 1 at the bottom. So vertices, there are 6. And that's the answer to question number 3, understanding vertices as well as edges. I never wrote edges there, did I? So that one, and I'll put it right there too. So we've got vertices and edges. All right, we'll go on to the next one. All right, welcome again. Here's another problem. This one deals with radians as well as the first time that somebody calculated the circumference and the radius of the Earth. Happened a long time before. Most people tend to think that people thought the Earth was flat. We don't have any record of general society ever really thinking that, just random people saying it, which it could be hyperbole because it feels flat from our perspective. Anyways, let's talk about it. On the summer solstice, Estrasthenes observed that the sun rays shone vertically and directly into a well in Cyrene. In Alexandria, at the same date and time, the sun cast a shadow. And Estrasthenes calculated that the sun's rays fell at an angle of 7.2 degrees from vertical. If Alexandria and Cyrene are 490 miles apart, use this information to calculate the radius of the Earth. Wow. We can just use these 2 numbers to calculate the entire radius of the Earth. First, just think about how cool that is. And secondly, let's go through the problem. So looking here, the sun's rays are going straight vertically at his first city, at Cyrene. But then in Alexandria, the sun's rays are not vertical. This angle here is 7.2 degrees. Now, because that angle is 7.2 degrees, we know that this central angle here is also 7.2 degrees. But that central angle, and I actually just am going to get rid of that symbol, that central angle at 7.2 degrees tells us a little bit more information as well. We've got 7.2 degrees. And one of the things that you'll learn, you'll be introduced to later in geometry, and you'll learn is far more useful than degrees, is this idea of radians. Radians are far more useful than degrees because they measure a circle based on a relationship for the circle. And let me just quickly kind of explain what a radian is. Here is the radius of a circle. A radian works like the radius, but you kind of curve around the outside of the circle. Turns out that if you keep doing that, curve, 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 you'll end up with 6.14 radians around the circle. 6.14 arcs of that same radius that go around the circle. And so we can actually use that understanding to help us to see how to shift from degrees to radians. It turns out that degrees, if you take degrees and divide by 360, that's the same thing as taking whatever radians we have. Usually we use R. We also use this symbol here, theta, to describe our radians, divided by 2 pi, because around a full circle, that's 2 pi radians. So if I want to solve for theta, I do 7.2 degrees divided by 360 degrees times 2 pi. Okay, if I go ahead and multiply those, I'll get a good radian value for that angle. And it'll be real useful to get that radian value. We'll see it in y in just a sec. So I'm doing 7.2. The degrees will cancel out, divided by 360. And then we're going to come over here and we're going to multiply it by 2 pi. So this equals 0.1256 radians. Now, just in case you're curious, 7.2 over 360 times 2 pi, you can actually simplify that out and cancel it. We would do 7.2 divided by 180 times pi. 7.2 divided by 180, I'm not sure exactly what that is, but let's go ahead and see what we get. 7.2 divided by 180. 7.2 divided by 180 is 0.04, or 4%. So this is going to be 0.04 times pi to be a more exact answer. All right. Now that we know that, how are we going to get the arc length? We know what this angle is in radians now. The angle in radians is 0.04 pi. So how are we going to get it in, how are we going to get this actual radius of the Earth? Well, it turns out that there's one more formula that you're going to learn, and this is arc length. Arc length. I put A with a lowercase, or with an L next to it in the subscript. Arc length. Now, in degrees, arc length is a long calculation, but in radians, it's a real easy calculation. It is the degree in radians multiplied by the radius. So if I want to solve for the radius, all I need to do is divide both sides by theta. Okay? And so I get the arc length divided by theta. Arc length divided by theta is equal to my radius. Those will cancel out, of course. So I just need to get my radius by taking my arc length, and we know what that arc length is. In case you're not aware, the arc length is the distance on the outside of the circle. It's this distance, and we know what that is. That is 490 miles. So I'm just going to do 490 divided by 0.04 pi equals r. Okay? Now, if I go ahead and divide that, I'm going to grab the calculator real quick, and I do 490 divided by 0.04 pi. And I get the radius of the Earth to be 338.99, or 3899.2, actually 0.30 miles. Okay? That's rounded to 2 decimal places. The radius of the Earth. 38, and I'm going to write it in a slightly bold color. That's 3899.30 miles. That is a pretty big radius. All right. We'll go on to the next one in just a moment. Now we're on to problem number 5. Let ABC have vertices at ABC. Let XYZ have vertices at X, Y, and Z. Are the triangles similar? If so, what's the scaling factor? Now let's take a look at these triangles and determine if they're similar. If they are similar, we could use one of these 3 methods. So this is something that should be going through your head. Oh, similar. I know shortcuts. Angle, angle, side, 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 or side, angle, side. Notice how angle, angle requires an angle. Side requires 2 sides and an angle. Side, side, side requires 3 sides. Looking at what we have, we don't have any angles at all, so that one won't work and that one won't work. The only one that'll work is side, side, side. So we need to see if those 3 sides share the same ratios. And in order to do that, what we're going to do is make a lot of slope triangles. Now, we can make slope triangles just like this. Oh, that did not work out. Let me see. Let me use a highlighter real quick. We can make slope triangles just like this. Okay, there's a slope triangle, so we can get the horizontal distance and the vertical distance, or we could use the distance formula. Now, way back in chapter 1, you guys learned the distance formula. The distance between 2 points on a grid is equal to x2 minus x1 squared plus y2 minus y1 squared. In the same way that we would use the Pythagorean theorem on this slope triangle. So let's apply it to this slope triangle using the coordinates for A, that's -2, 0, and the coordinates for C, that's 3, 5. All right, so notice in this figure, it goes up 5, and it goes over 5. So this is a 5 by 5 slope triangle. Now, if I use a squared plus b squared equals c squared, I know that this is 5 squared plus 5 squared. So 5 squared plus 5 squared is 50. 5 squared plus 5 squared is 50. So we know that the distance from A to C is going to be the square root of 50 using the Pythagorean theorem. Now, using the distance formula, I'm going to produce the same result. But the distance formula allows me to do it without actually calculating by drawing the figure or anything like that. All I got to do is look at my coordinates for A and C. Now, for A, I've got -2, 0, and for C, we have 3, 5. So I'm going to put AC is equal to the square root of -2 minus 3 squared plus 0 minus 5 squared. Notice how I just used those coordinates. -2, 3, and 0, and 5. Boom. So now I can go ahead and do this sum of these in the square root. Notice how it becomes 5 squared, or -5 squared, plus -5 squared. Now if I square a negative number, it becomes a positive number. So this really becomes 25 plus 25, which is equal to the square root of 50. So I'm trying to find out if the other length has the corresponding one. Using the distance formula makes this a lot quicker, and it's pretty easy just to plug in. That's what I'm going to do for the next few. I'm going to write them out, and then I'm going to plug them in. AC is equal to the square root of 50. Well, what about the other lengths? What about AB? So AB is equal to the square root of -2 minus 2 squared plus 0 minus 5 squared. Okay, -2 minus 2 squared is -4, so this becomes the square root of not -4, but -4 squared, which becomes 16, plus 5 squared, which is 25. So this is equal to the square root of 41. Very nice. And then finally, what about, let me get rid of this so we can actually see it correctly. That's AB. Now, what about BC? Well, BC is real easy because you go from 2, 5 to 3, 5. We just go over 1. So we've got those 3 lengths. Now what we need to do is compare that to the lengths for XYZ, XY, XZ, and YZ. All right, I want to compare those lengths, so we're going to do xy right here. To do xy, we're going to go ahead and take 0, 4. This will be the square root of 0 minus 0 minus 10 squared plus 4 minus negative 4 squared. Notice those two negatives form a positive, so that's really 4 plus 4. Then we end up with the square root of 10 squared, technically negative 10 squared, but we know that it's going to become a positive, plus 4 plus 4, which is 8 squared. Okay, putting those in there, we get the square root of 100 plus 64, 164. Now looking at that 164, hey, isn't that 4 times 41? That's the square root of 4 times 41, which is equal to 2 times the square root of 41. So that's xy. We also need to find out what xz is and what yz is. We'll do the easy one next. What is yz? Yz goes from 10 comma negative 4 to 10 comma negative 6, so that's 2. Notice how that's 2 times BC. And then this one, xy, is 2 times AB. So let's go ahead and find out the last one. We want to find out xz. What is the length from x to z? Xz is equal to the square root of 0 minus 10 squared plus negative 4 minus negative 6 squared. Actually, I did negative 4 because I was looking at y. It should be just 4 minus 6 minus negative 6. So we end up with the square root of 10 squared, which is 100, plus the square root of 10 squared, because 4 minus negative 6 becomes 4 plus 6, so that's another 100. So this is the square root of 200, which becomes the square root of 2 times, students just came in, I got a little distracted. Square root of 100 times the square root of 2, which becomes 10 times root 2. Now, looking at this one, we've got something a little interesting. That's the square root 50. But the square root of 50 doesn't look like 10 times the square root of 2, but it can break down. It can be the square root of 25 times the square root of 2, and the square root of 25 is 5, so it's 5 root 2. Notice how this is double. So it turns out that these two triangles are similar using side, side, side. Take a quick look at this. We've got 5 root 2 over 10 root 2. That's the same thing as 2 root 41 over, I did that backwards, sorry. Root 41 over 2 root 41. And that's also equal to 1 divided by 2. All three of these are equal, so the triangles are similar by side, side, side. So triangle ABC is similar to triangle XYZ by side, side, side similarity. All right, we'll work on some more problems in just a moment. Here we are, continuing on in problem number 6. It starts with the vertices of a triangle lie on 2 parallel lines. Ooh, the lines are parallel. Make a note of that. Put some symbols on it. Parallel, parallel. Those 2 lines are parallel. Okay, so given the values of 63 and 72 degrees, determine the angles y and x. Now, you should be able to quickly recognize some things about these angles, specifically that you've got angle relationships. Parallel lines, this is a transversal, so you should recognize you've got parallel lines cut by a transversal, so you've got lots of relationships. In particular, notice how 63 is on the inside, and so is Z. Those are alternate interior angles, or AIA, alternate interior angles. That means this is 63 degrees as well, because it's in between parallel lines. Awesome. So what is y? Well, if I use the trisum theorem, I could find out what the measure of angle y is. So 72 degrees, 63 degrees, and y. So I'm going to take 180 minus 72 minus 63. I just did 36. It's minus 72 minus 63. And I end up with, I'm just going to use a calculator real quick for that. 180 minus 72 minus 63. And so I end up with 45 degrees. Using the triangle sum theorem, this is 45 degrees, TST. All right. Being able to find out those angles using different methods is very useful. One of the other methods you could use is recognize that these two angles add up to 100 and, what is it, 100 and, oh gosh, I can't remember, 135 degrees, I think. So those two angles add up to 135, and they're same side interior with this one. So you could have used same side interior angles to get that as well. There's not a single way to get each answer. There's multiple ways, but this is the way that I chose. So the triangle sum theorem and then alternate interior angles, these were going to be congruent because they're alternate interior angles. The other one is the trisum theorem. We couldn't use alternate interior angles here because notice how this angle doesn't alternate with an angle that we know. Of course, we could have found it by knowing that these add up to 180 and subtracting out from those. And we are on to problem number 7. Assume that ABCD in the following diagram is a parallelogram. Let's go ahead and add those arrows to communicate that it is a parallelogram. All right, and that points AD and F are collinear. If angle B is 120 degrees, let's add that detail. 120 degrees. And angle F is 25 degrees. That's that one. Find the measure of angle DCF. So we want to find out what this angle is. All right. So what do we know? Well, since it's a parallelogram, we have all those properties of a parallelogram. We don't care about the side properties so much because we're just dealing with angles and we want to find an angle. We care about the angle properties. And the big one that we can use here is the idea that in a parallelogram, opposite angles are congruent. So that means if angle B is 120 degrees, then angle ADC is 120 degrees as well. Opposite angles are congruent. Now, noting that these are collinear actually tells us that this is a line. It's not goes up and then goes up like that. So we know that if this is 120, this has to be its linear pair, which it means that that is 60 degrees. Oh, look. Now I've got a triangle and I know two angles. So if I use the triangle sum theorem, the trisum theorem, then I know that I can take 180 minus 60 minus 45, and I end up with 95 degrees. That third angle is 95 degrees. And now I know the measure of angle DCF, but I do want to state it. The measure of angle DCF is equal to 95 degrees. Notice how we're always stating our answers, making sure they're clear. Problem number 8 here is a fun one. Two circles of center O and O prime intersect at A and B. The length of a common chord, AB, is equal to 10. So we know the length of this is 10. Okay, the line joining the centers intersects the circles at P and Q. So the line joining the centers, these two, intersects at P and Q. If PQ is 2 and the radius of one circle is 13, find the radius of the other circle. So let's go ahead and do this. First, we know that this length is the radius of a circle, so that is 13. But that radius is copied over here. That is 13 as well. Wait a second. That makes this an isosceles triangle. And in an isosceles triangle, we know that first the base angles are congruent. Not too helpful here. We also know that any point on this isosceles triangle, this creates a perpendicular bisector of AB. Now we know that AB is 10, which means that this length is 5 and this length is 5. And here we've got another Pythagorean triple. This and this, that makes this length from from O to T 12, because we know that it's a 5, 12, 13 Pythagorean triple. So we've been through 2 Pythagorean triples in these sets of problems themselves. We have a 3, 4, 5 triangle, not multiplication, but 3, 4, 5 triangle, and a 5, 12, 13 triangle. These are 2 Pythagorean triples. Now, I'm going to erase the bottom part here so we can just focus on the top part. We know that this distance here is 12. That's good, from O to T. All right. So what else do we know? We know that that's 5, and we want to find the radius of this circle. So I'm going to actually highlight that circle with this color. And I'm going to be like, what's the radius of that circle? Now, knowing that it's 13, and knowing that QT is 12 actually tells us one more thing. That is this. Q to P is 13 because that's a radius of the circle, just like QA, or OA is. I keep saying Q. OA and OP are both radii to the circle, so they're both 13, which, if this length is 12, that makes this length 1. So we're going to put a 1 there. Now, if that's 1, and we know that QP, which is written up here, QP or PQ is equal to 2, we know that this part is also 1. Now, if I take a look at that, that actually tells me all I need to know about this figure, because that means that even though it's not drawn to scale, this and this are symmetric. The distance from a single point to each end of the circles is the same, which means these 2 circles are symmetric at where they intersect. These 2 circles have the same length, and we got to remember these circles are not drawn to scale. So that means that this distance from T to O prime is also 12. I know it doesn't look it, but it is, because again, these are not drawn to scale. And since that's 12, that means this has to be 13. So the radius of the second circle is also 13. Take a moment to re-watch this part of the video. It's a little hard to understand. And we'll go on to the next one in just a moment. All right, we're on to question 9, which is the intersection of 4 semicircles of radius r defines a flower shape with 4 petals. What is the radius r if the total area of the flower is 2? Now, in understanding that, first we want to understand that the area of the flower is equal to 2. We're going to put that off to the side. Another thing to understand is that these are circles. So here's the first circle, and it might not fit exactly because this is a printed sheet of paper. It probably won't perfectly match up. So there's the circle. Notice how this circle has a center right about there. Might be a little bit higher, a little bit lower, but we understand where the center is. And then the radius of the circle, we could go right down to here and find out what that radius is. Okay, I'm going to get rid of the circle so we can work with this a little bit easier. Now, that's what I want to find out. I want to find out what this r value is right here. And in order to do that, first thing I'm going to do is make a square. Now, I know that it's a square because both dimensions are going to be equal, and I drew that really badly. Let me go ahead and draw that again. I'm going to get rid of this and that so I can try and draw my square a little bit more effectively. That is a rectangle, but it'll work out to help us make a square. All right, so we have a square. Now, because each of these lengths from here to here, here to here, and here to here are all the same, that means they're all radii. And the area of this rectangle is equal to is equal to r squared. I got a little ahead of myself. But then I want to find out the area of just this portion, which I'll show you in just a sec. I want to find the area of just this portion right here. Notice how that's not a square. That is a quarter of the full circle. If you were to think about drawing that full circle again, that's 1/4 of that full circle. So we know the area of 1/4 of the circle is equal to pi r squared. That's the area of a circle, but then we have to multiply that by 1/4. That simplifies to pi r squared over 4. Now, let's say I want the area of the pink part. Just the pink part. If I want the area of just the pink part, I'm going to get, and I'm going to draw it right here, the area of the pink part is equal to the area of the square minus the area of the quarter circle, pi r squared over 4. That's how I can get the area of that portion of my section. So how do I get the area of this section? Well, one thing I'm going to do is realize that this will get me this section. If I do it again, I can get this section. So I'm basically doing this twice, or multiplying that by 2. So I'm going to draw that. The area of this section and this section is equal to 2 times the radius squared minus pi r squared over 4. Okay? So the area of both of those sections is equal to that. Well, what I really want is the area of this petal. So how do I get that? Well, the area of the petal is really equal to the square minus that pink part. 2 times the radius squared minus pi r over 4. And now that I know the area of one petal, I can get the area of all 4 petals by putting these all together. So we're going to come back over here. The area of the flower, that's all 4 petals, is 4 times this. 4 times r squared minus 2 times r squared minus pi r squared over 4. All right, because there's 4 different petals, by subtracting out that pink part twice, we get the center petal, and then by multiplying that by 4, we end up with the area of the whole flower. Now, you might notice that there's a lot of stuff we can factor out here, and that's what we're going to do. First things first, we're going to multiply and distribute this 2, though. See what happens whenever we take that 2 and distribute it to both terms. We end up with 4 times radius squared minus 2r squared minus pi r squared over 2. And notice how there's a radius in each of these, but there's also a 4. So I can factor out the radius. I can multiply both sides, or distribute out the 4. I'm going to distribute out the 4 first, so we kind of see what happens there. So distribute out the 4, we get 4r squared minus 8r squared minus, oh, and I forgot to distribute the 2. So this should actually be plus right here. Actually plus right here, because we distributed negative 2. Okay, so 4r squared minus 8r squared plus pi r squared times 2. Because if we have 4 divided by 2, we get times 2. All right, so now that's distributed. And now we're going to factor out some terms, combine like terms. So notice how we have 4r squared minus 8r squared. That's really negative 2r squared plus 2 pi r squared. And we can go ahead and factor out the r squared. By the way, this should continue to be equals. So we get r squared times negative 2 plus 2 pi. Okay. Now, we typically like to rearrange these terms. So I'm going to rewrite this as r squared times 2 pi minus 2. Okay. Just rearranged everything. And then finally, we know that that's equal to 2, because that's the area of the entire flower. That's equal to 2 of those. So how do we solve for r? Well, let's go ahead and divide out this part from both sides. Now I'm running out of a little space, so I'm going to zoom in and put it right over here. This 2 divided by, and I'm actually going to write it like this, r squared is equal to 2 divided by 2 pi minus 2. Pretty good. Notice how there's a 2, a 2, and a 2. I can factor that out, cancel out the 2's. So I end up with r squared is equal to 1 over pi minus 1. And then I need to take the square root of both sides. So r is equal to the square root of 1 over pi minus 1. Now the square root of 1 is going to be 1, so we can go ahead and write that. We know our radius is positive. It's not going to be a negative 1. So it's going to be 1 over the square root of pi minus 1. Whew. Now another way to write this is that the radius is equal to, let me actually just show you how to multiply this. This has an irrational denominator, so we want to put it in the numerator. That becomes times pi minus 1 over pi minus 1 over the square root of pi minus 1. And notice how the bottom, the square roots will cancel because they're multiplied together. And I'm really multiplying by the number 1, so it becomes the square root of pi minus 1 over pi minus 1. That would be the radius of my circle if the area is 2. All right, with that said, that was a long problem. This is the type of problem that you wouldn't encounter in a regular geometry class. It's just an extreme adaptation of using the area of different figures, doing subtraction, applying square roots, and combining like terms. A lot of algebra and geometry put together. All right, have a good day. Here we are on problem number 10. Triangle ABC with side lengths 12, 5, and 13 is extended to a similar triangle ACD as shown below. What is the area of the larger triangle ACD? So we want to know the area of this giant triangle. And if you know your triangle similarity, which you covered in chapter 7, you would recognize that this giant triangle is similar to this right triangle. And it's also similar to this right triangle. The reason we know that this is a right triangle is this is a Pythagorean triple. That is a 5, 12, 13 triangle. 5, 12, 13 triangle means that it has to be right. And that's because 5 squared plus 12 squared equals 13 squared. So this is a right angle here. We know that that's a right triangle. Since the large triangle is similar, we know that this is a right angle. And then since the small triangle is also located here, we know that that also has to be a right triangle. Awesome. Well, how would we go ahead and find the area of the large triangle? Well, the area of the large triangle is going to be base times height. We already have the height of this triangle. That's the altitude, and let's make a note of that. The altitude goes from a vertex, and it's perpendicular to the opposite side. Typically called the height of a triangle. All right, so we know that the altitude is 5, but we need to know the base, which means we need to know the length of BD. Fortunately, since we know that these triangles are similar, we can create a ratio. Let's call this length across the bottom x. Okay? And now if I look at the medium triangle and the small triangle, I can create equivalent ratios. I know that 12 under 5, the short length, short side, or short leg divided by the large leg, or long leg, of the medium triangle is going to be the same as the short leg of the small triangle divided by the long leg. Solving for x here, I get 25 over 12, which is, I believe, actually, I'm just going to divide it using Desmos real quick. And 25 divided by 12. 2.08. Okay, so I end up with that as the length of this side, 2.08. All right, so now I know my entire base. My entire base is 12 plus 2.08. Summing that together gives me 14.08. And so now I can get the area of the larger triangle. The area of the larger triangle is equal to the base times height divided by 2. The base is 14.08 times the height, which is 12 divided by 2. Now, you can plug that into a calculator to get the result. We're going to go right on to the next problem. And we only have 2 problems left. Here's number 11. Trapezoid ABCD has diagonals connecting corners, and the resulting angles are, angle W is 30 degrees. Let's go ahead and write these down. That's 30 degrees. Angle R is 35 degrees. Angle Y is 45 degrees. Angle Z is 25 degrees. And we want to find out what angle X is. Find the value of the angle labeled X. How do we go about that? Well, it's a trapezoid, so we can't use parallel lines and alternate interior angles, though it almost looks like we would want to because Y and X are almost alternate interior. Technically, they're alternate interior angles, but these lines are not parallel. So since we don't know if those lines are parallel, we can't really find out what X is off the bat. What we can do is use what we know about angles Y and R and this shape. That is a triangle. So we can go ahead and use the trisum theorem to determine what that angle is. I know that Y and R plus that third angle add together to be 180. So if I do 180 minus 35 degrees minus 45 degrees, I could find out what my remaining angle is. Now, let's pull out this one. We got 180 minus 35 minus 45, and we got 100 degrees. So we know that that angle is 100 degrees. Well, that angle is actually related to the angle right across from it because they are vertical angles. So since that's 100 degrees, this one is also 100 degrees because they are vertical angles. All right. Now, if that one's 100 and that one's 25, what does that one have to be? Once again, apply the trisum theorem. We got 180 minus 100 minus 25. And so that becomes 180 minus 125. And just to show you that real quick, 180 minus 125. I put times. Oof, that was a lot bigger than I thought it would be. 125. That's 55 degrees. So that angle X is going to be 55 degrees. And we'd write it like this. The measure, wrote it backwards. The measure of angle X is equal to 25 degrees. Actually, that's a little bit off. Notice how X is the measure of the angle. The name of the angle would be CBD. So I'm going to just say X is equal to 25 degrees. That would be the most accurate way, or 55 degrees. Ooh, that would be the most accurate way to write it. All right, one problem left in this section. All right, here we are, on to question number 12. How many 2x1 tiles can be placed on an 8x8 checkerboard after 2 of the opposite corners of the board have been removed? So notice that this one is removed, this one is removed. So how many tiles can we place? Well, let's go ahead and just kind of imagine placing a tile. Each tile takes up 2 spots next to each other. They're 2x1. So we've got 1, 2, 3. Ooh, that last one won't really fill in, will it? Maybe I can go down like that. And then that's 4, 5, 6, 7, 8. Oh, I got to keep going down like that. Okay, that's not necessarily a problem. Now it looks like, if I were just to think about this, since they're 2x1 tiles, couldn't I just take 62 and divide by 2? And get the number that they would fit, 31? Is that correct? Well, let's keep working at it and find out. So far, we've got 1, 2, 3, 4, 5, 6, 7, 8. So we're going to keep going. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4, 5, 6, 7. Oh, it's right there. Huh. That might be a little difficult to deal with. Let's add these on at the end. 8, 9, 30. Huh. What if I take this one and move it over here? Then I still got the problem because notice how they're catty corner. I can't put one tile diagonally there. I've got to kind of do something else. So you'll notice that this problem kind of persists throughout the whole problem. We can't get these to line up. Because there's those two opposite corners that are missing, the number of tiles is not going to be 31. You're only going to be able to fit 30 tiles. Only 30, since the last two cannot match up. And that is the big deal here. Those last two tiles just can't match up. And let me highlight these so we understand that in a little bit clearer way. This tile and this tile will never be able to intersect. And so we know that there can only be 30. With that said, I will talk to you later. We'll go on to the next one next week. Have a good day.